Now let us see the problem. A rod 150 centimeter long and diameter 2 centimeter is subjected to an axial pull of 20 kilonewton. If the modulus of the elasticity of the material of the rod is 2 into 10 to the power 5 Newton per mm square, determine case 1 the stress, the second one the strain, and the third one the elongation of the rod. The given data in the problem is the length of the rod L is equal to 150 centimeter, the diameter of the rod is equal to 2 centimeter, then axial load is equal to 20 kilonewton, and Young's modulus capital E is equal to 2 into 10 to the power 5 Newton per mm square. We have to find stress. Stress is equal to sigma is equal to load divided by area. So load is equal to 20 into 10 to the power 3 Newton per mm square, 20 kilonewton, divided by area is equal to area of the rod is equal to pi by 4 into d square, diameter is equal to 20, therefore area of the rod is equal to 100 pi mm square, therefore stress is equal to 63.662 Newton per mm square. So next we have to find strain. Strain is equal to change in length divided by original length. We have to use by using Young's modulus formula. So Young's modulus is equal to stress divided by strain. Therefore, strain is equal to stress divided by Young's modulus. So stress is equal to 63.662 Newton per mm square divided by Young's modulus 2 into 10 to the power 5 Newton per mm square. Therefore, strain is equal to 0.000318. So strain is unitless. The third one we have to find the elongation of the rod, dou L. So dou L is equal to strain into length of the rod. So therefore strain is equal to 0.000318 into length of the rod is equal to 150 centimeters. Therefore dou L is equal to 0.0477 centimeter. Next problem, an axial pull of 35,000 Newton is acting on a bar consisting of the length as shown in figure. If the Young's modulus is 2.1 10 to the power 5 Newton per mm square, determine stresses in each section. The second one, total extension of the bar. The given data of the problem is axial load P is equal to 35,000 Newton. The length of section 1 L1 is equal to 200 mm, and diameter of section 1 D1 is equal to 20 mm. The area of section 1 A1 is equal to pi by 4 d square. The diameter is equal to 20, therefore 100 pi mm square. The length of the section 2 L2 is equal to 250 mm. The diameter of the section 2 D2 is equal to 30 mm. Then area of the section 2 A2 is equal to, the diameter is equal to 30, therefore area 2 is equal to 225 pi mm square. The length of the section 3 L3 is equal to 220 mm. The diameter of the section 3 D3 is equal to 50 mm. Then area of the section A3 is equal to the diameter 50, therefore area of the section is equal to 625 pi mm square. The Young's modulus capital E is equal to 2.1 in 10 to the power 5 Newton per mm square. So we have to find stress in each sections. So stress for section 1, sigma 1 is equal to load divided by area of section 1. So P divided by area 1 is equal to 35,000 divided by 100 pi is equal to 111.408 Newton per mm square. Stress in section 2, sigma 2 is equal to load divided by area 2, therefore 35,000 divided by 225 into pi is equal to 49.5146 Newton per mm square. Stress in section 3, sigma 3 is equal to P divided by area of 3 is equal to 35,000 divided by 625 into pi is equal to 17.825 Newton per mm square. Therefore, we have to find the total extension of the bar. So dou L is equal to P divided by E bracket of L1 divided by A1 plus L2 divided by A2 plus L3 divided by A3. So therefore 35,000 divided by 2.1 into the graph 3 10 to the power 5 into bracket of 200 and L1 is equal to 200 divided by area 1 is equal to 105 plus L2 is equal to 250 divided by area 2 is equal to 225 into pi plus L3 is equal to 220 divided by area 3 is equal to 625 pi. So therefore the total extension to L is equal to 0.13 mm. The third problem, determine the value of Young's modulus and the Poisson ratio of a metallic bar of length 30 cm. So breadth is equal to 4 cm and depth is equal to 4 cm. When the bar is subjected to an axial compressive load of 400 kN, decrease in length is given as 0.075 cm and increase in breadth is 0.03 cm. The given data of the problem is, so length is equal to 30 cm, the breadth is equal to 4 cm and the depth is equal to 4 cm. The area of cross sections area is equal to breadth into depth, therefore 16 cm square, therefore 1600 mm square. The axial load is equal to 400 kN, then decrease in length dou L is equal to 0.075 cm, increase in breadth delta B is equal to dou B is equal to 0.003 cm. The strain change in length divided by original length is equal to 0.075 divided by the length of the rod is equal to 30, therefore 0.025. So strain is useless. Next one, lateral strain. So lateral strain means change in breadth divided by original breadth is equal to change in breadth is equal to 0.003 divided by original breadth 4 centimeters, therefore 0.00075. Therefore Poisson ratio we have to determine the Young's modulus and the Poisson ratio. We have to find the Poisson ratio. So Poisson ratio is equal to lateral strain divided by longitudinal strain. So lateral strain is equal to 0.00075 divided by longitudinal strain is equal to change in length divided by original length, therefore 0.0025. So therefore the Poisson ratio is 0.3. Next one, Young's modulus. So Young's modulus capital E is equal to stress divided by strain. Therefore stress and longitudinal strain, Young's modulus is equal to stress divided by strain. Therefore strain is equal to stress divided by Young's modulus. Therefore so stress is equal to P divided by area into Young's modulus. So therefore stress is equal to 0.0025 is equal to 400 kilonewton divided by, so area is equal to 1600 mm square into Young's modulus. So therefore Young's modulus is equal to 400 kilonewton divided by 1600 into 0.0025. Therefore so Young's modulus is equal to 1 into 10 to the power 5 Newton per mm square.